Let me continue now. So let's take a look at the queue. So let me first explain quickly how the insert and the delete are working, the code. So I go back to the slide now. So here we have the insert. So the insert is doing this funny operations here. But let me show you how it works by presenting a queue. So let's say we have a queue where we have N and we have A, B, C. Let me put a variable here. F1, F2, F2. So let's say this is our queue with A, B, and C. And we will now first do this. That means we will bind this to F. So this is the F. And we will bind this to X, B2. So what does this do? So notice that F2 is the same here. So I'm binding F2 to XB2. That means the new operation will be Q. And then the here I will have F in the output. So that's A, B, C. And then I will have F2. But notice F2 is equal to XB2. So that's going to be equal to DX if I add or BB2. And then notice that I will put B2 here. So notice I have actually added D. So basically by binding the back, here I bind the back, I've added it. And I have to do an assignment now to put the new value of Q. And of course the N becomes N plus 1. So I have two cell operations, so I put them inside a lock. So the delete, show you how the delete works, but let me just show very quickly. Here this X bar F2 will be bound to the front of the queue. So if it's A, B, C with something, F prime, then this will bind it to X bar F2. So you see the X gets bound to A and the F2 goes to the rest. So this will actually get the first element. Of the queue. Okay? And then I will create a new output where F2 is going to be just the initial value without the first element, and the back stays the same. So this removes D. So here I will have X is equal to A. Okay, so this is how the insert and the delete work. I can actually write the code here. So let me write the code for you. So is that okay? What happens if the queue is empty and we call delete? That's a very good question. I will answer that question in 5 minutes. Okay? This is a good question. Just answer minutes. There's actually a slide on that. What happens if the queue is empty and we call delete? So it depends what we want there. So I will answer that question in 5 minutes. But let me go first to the code here. Let me implement now a queue. Concurrent queue. So I will create this new queue function. Now cells and locks are part of the system, so I can create a cell immediately. I will also create the lock. New lock is part of the system. Okay, and now I will have the insert. Let me first write the skeleton of the code. Delete. And then I return a tuple. It's actually a record with the insert and delete operations. Okay, so this is the queue. Now let me do the insert operation. So the insert, it has to do a lock. Okay, the delete also has to do a lock. Let me first put in the lock. Okay. And inside this lock, I will now read the cell which contains the queue, and then I will update the cell. So reading it, I will actually do a kind of pattern matching. I will bind the tuple to the value of the cell, and then I will update the cell to give you the new value. So the new value will be n plus 1. Then f is the same, but I've bound the back. Here you can see that this was actually the back. I've bound it to x b2, so the new back is b2. Okay. Of course, now I have to declare the new variables that I've used. So I have to put in the new identifier. So n, I'm using n. I'm using f. I'm using b2. X is an argument. Okay. So that's insert. And now the delete operation. So here again I have q, n, but now I need to traverse the front. So x bar f2 will be equal to the front. So the x will be bound to the first element, f2 will be bound to the remaining elements. And then I update the new content. Here I have now n minus 1. f2 is going to be the new front. You see the x is removed from it. And I have b. Of course, I have to declare some identifiers here. N, f2, and b. I think that's all. Huh? So this is my queue, and it's using one cell and one lock. Okay, I hope I've done it right. And now we can actually use it in different threads. So, for example, we can declare q is equal to new q. Here we have a q. And then we can do insert. So we have, q dot insert. We can do a, put a in there. I think I've made a mistake. What is wrong here? Insert. Of course. Very dumb. The new cell is not 0. It has to be a tuple, 0, 0xx. Okay, you see that? I fixed it. The initial value is not 0, of course. That was completely stupid. It has to be an empty q there. So I fixed it now. New q. Now I insert a. And now I can delete q dot delete x browse x. Okay, and this will give me a here on the left. Okay, and the insert and delete can be called from multiple threads. So you see how it works. Is that clear? What happens if the queue is empty and we call delete? Okay, I will get to that. There are some people doing guessing what the answer is. One person says it will cause deadlock. Other one says I think it will wait for a value of the queue that looks like h bar t, so that it will wait. Okay, so we'll see now what happens. Actually, what's going to happen is something very smart because of single assignment binding. Let me first explain why we need reentrancy, and then I'll explain what happens if you do delete on an empty queue. So I actually already explained why we need reentrancy. I explained why the critical section can consist of two parts, but I did not explain yet why that when you enter a lock and you're inside, sometimes you have to enter again the same lock. And here's an example of why you do it. Let's extend our queue abstraction. So let me now implement insert 2. I want to put two elements in the queue, x and y. But I want them to be together. and nothing in between. So I call insert X and insert Y, but the scheduler can always stop in between. Okay, if I do this, because insert X, insert Y are atomic, but insert 2 is not atomic. But I want X and Y to be in there at once. So for example, the queue models people waiting in line. 2 people arrive, they're friends, they both go in the line. I want to guarantee that they will be next to each other in the line. Okay, so I want to guarantee that the scheduler will not stop in the middle. How do I implement that? Well, I have to use the lock. So I put in a lock, the lock L, and insert X and Y are now protected by the lock. I have now one big atomic action. But we have to be careful here, because when we go in and we enter this lock, when you call insert, there's another lock inside the insert in there. So what should happen? Well, logically, we are already in the lock. So if we try to go in again, it should be okay. It should be acceptable because we're already in. And that's what a reentrant lock does. Reentrant means that if you're in the lock, that you're allowed to re-enter. You're re-entrant, you're allowed to enter again. Sometimes it's called thread reentrant lock. Sometimes people put the word thread before. That means if a thread is inside the lock, it can go again. You can see that this allows us to build abstractions in an easy way. You see that we can build insert 2, we can use the lock, we can add more locks, and everything is fine because the lock is reentrant. Okay? If we're in the lock, we can go in again. So the lock has to be reentrant. All the locks in practical systems will be reentrant. So locks in Java synchronized objects, for example, they are reentrant. So all practical locks in real systems will be reentrant. Okay? So that's the first thing. But now let's come to the question, what happens when you do delete on an empty queue? Actually, our implementation is very smart in this case. What you want to happen in our implementation, you can actually delete elements before they are inserted. So the number of elements in the queue can become negative. So if you do delete X on an empty queue, the queue will have -1 elements. So what does that even mean? It means that we have a placeholder. So the X will be in the queue, and the next time we do an insert, we insert AAA, for example, then that will be the element. At that moment, X will be bound to AAA, and Q will have 0 elements. So it's like a debt, a promise that the next element we insert will be X. Okay? You can actually verify this by running delete X on an empty queue. So this is an advantage of single assignment. So single assignment has many advantages. It lets you build agents that have no memory leaks and tail recursive list functions and so on. This is another advantage. It allows you to do many operations without blocking. Okay, so I would suggest as an exercise to do this. Run delete X on an empty queue and see what happens. Okay, what F and B. Notice that they will be bound, of course, but how they will be bound will actually create a placeholder. In fact, if you put elements in a queue, then elements come into the front. But if you delete elements from empty queue, the negative elements are put in the back. Okay, they will fill up the back, and when you start inserting, it comes back to the front. So this is a property of single assignment. Now, if you don't like this property, if you want the queue to block, when you delete from empty queue. So if you build a queue without this property, if you build a queue where it has to have 0 or more, then you want the queue to block. Here you will have to do it explicitly. You will have to put an explicit wait x. So if x is unbound here, that means the element is not yet inserted. Then you will wait. So the wait x will wait until the operation is bound. Okay. Okay. This property of deleting before inserting is not essential to the course on concurrent systems. It's a property of this very nice queue implementation. So this is actually a very nice queue implementation. So I'm not going to spend so much time explaining exactly how it works. If you're curious, you can investigate, and I can talk to you about that after. But I would like to continue talking more about concurrent system. Okay. So let me go back to the chat. So it's actually a very nice queue implementation. Okay. So there's a whole bunch of discussion on this. It seems that people are very interested in this. So there's a question, is it possible that after insert X, another thread managed to execute insert before insert Y is executed? Yes, that's the example of reentrancy. Yes, if you do not have an extra lock, that's what could happen. It seems very difficult, but not impossible. That's important. In concurrent systems, nothing is impossible, okay? If you think that the scheduler has to do exactly the right thing for the bug to happen, it will happen, okay? You can assume the worst. It will happen, okay? So in a computer, many operations happen per second. The queue can run millions of insert and delete per second. Any weird thing, don't worry, it will happen. You can assume that it will happen, okay? So let me now go on. Let me show you another implementation. Let me show you another implementation. Remember that I talked to you about exchange. The exchange does a read and a write atomically. We can actually implement our queue with exchange because we're only doing one read and one write for the data, okay? So whenever we do an insert or a delete, we're updating only once. So this is a very simple data structure. We're not doing many things. We're doing just one update, which means that we can implement the queue, insert and delete, using single exchange operations. Notice that this is actually very efficient, okay? Because we do not have to create the lock, enter the lock, leave the lock, and then do the two cell operations. We just need to do one exchange operation, okay? So if you look at the implementation here, the exchange, so this will be bound to the old content, and this second one is actually the new content. Okay, so you can see that it's doing both the read and the write. There is an interesting point here. The m, the new value here, which is n plus 1, this one has to be done after the exchange. The addition, the n plus 1, has to be done after the exchange. Why is that? Well, if you try to do the addition before the exchange, the n will not have a value yet because it's coming from the exchange. So the addition will block and the insert will block. Okay, it will have a deadlock, in fact. So the way to do it correctly is to first do the exchange. This will bind n, and then we put in an unbound variable. as M, and we bind it after. So you see the addition has to be done after the exchange. Otherwise, the system will deadlock because the n is not bound yet. And the same for the delete when you do n minus 1. Okay? So this is actually a very efficient queue. If you want to implement a queue in your programs, this is actually a very nice way to do queues. It's a very powerful queue that lets you insert and delete in constant time. It lets you delete before inserting and still be correct. And it does not need locks because it's using exchange. Okay? So this is a powerful concurrent queue. Of course, if you want to do insert 2, you will still need a lock, of course. You can't, it's not going to do magic. If you want to do insert 2, you will be doing 2 inserts. And that means 2 exchange operations. That means 2 operations. So you will need a lock, because otherwise the scheduler can still stop in the middle. Okay? So if you want to do insert 2, you will still need a lock. Okay? But for the simple insert and delete, you will have a very efficient operation. Okay, let me go back a second to the chat. Is that reasonable? So you can see now you get already one example of why exchange is so nice. Okay, why exchange is nice. But we will see a better example of exchange in a few minutes when we start implementing the locks. Okay, so now what we're going to do, I've showed you an example of how to use the locks in the concurrent queue. Now we're going to implement the locks, and you will see what goes on inside the lock. The magic of the lock, you'll see how it's done. Okay, so we're going to implement the lock now. Implementing locks, and we'll start by implementing simple lock and then reentrant locks. So the way we will implement the locks, a lock can be implemented using a cell, and the simplest way by far is by using an exchange operation. Okay, so the lock will need, the reentrant lock actually needs 2 cells, but a simple lock that is not reentrant can be implemented with 1 cell. So we will use a very powerful technique called token passing. So the way the lock works is we have to guarantee that there's only 1 thread inside. How can we guarantee that? Well, we have a special data item called a token. And we guarantee that there is only 1 token in the whole system. When a thread goes in the lock, it takes the token. When a second thread tries to get in, it tries to take the token, but it cannot because there is only 1 token. So it will wait. And when the first thread leaves the lock, it passes the token to the next one in line. So then the waiting thread gets the token and goes in. So the thread needs to get the token to get in. In French, it's called a jeton. So you have a thing which exists only once. And that thing will guarantee that you have exclusion inside the critical section. Okay? So token passing is a very powerful technique. In fact, it's used also in real life. If you go into a store or you go to Brussels Midi station and you have to get in line to buy a ticket, then you press a machine and it gives you a number, and you basically wait until your number is called. Okay? So you have a line of people waiting. Here you have a similar thing. You will have a line, a queue of threads waiting for the token. But only 1 thread will actually have the token. Okay? If a thread tries to get in, so there's only 1 token in the system. If it tries to get in without the token, it waits. And when a thread leaves, it passes the token to the next guy. So how do we implement the token? We're going to implement the token. There's many ways to implement tokens. Okay, if you want to implement this in Java, you can do it in one way, or in C, but we are going to implement tokens using single assignment. You can understand we have this very powerful single assignment concept, so we're going to implement tokens using single assignment. So here is a simple lock with token passing. So the token is actually going to be stored in a cell. And we're going to use this special constant value. So the idea is that if you have a bunch of threads trying to get in, so let me make a bunch of threads here. All of the threads want to get in. And each thread will get two variables. It will have an old one and a new one. And then the next thread will have old one and new. And this one will have old and new, and so on. Let me write and explain how it works then. Old and new. So the new value of one thread is equal to the old value of the next thread. Okay? So in order to get in, the old one has to be bound. So this is the token. So when T0 comes in, so the lock is here, I have a procedure. P here is the statement. So the P, it's actually going to use higher order here. Huh? So the P is going to be a zero argument procedure that contains a statement. So how does it work? Well, I use exchange to get the token. Okay, the exchange gives me the old value, and then I wait. I wait until it's bound. So the token means that the variable is bound. So here I will do a wait on old. So the first thread that comes in, T0, the first one, it gets the old value, which is equal to unit. It's very happy because he has the token, and he goes in and he executes P. Now the second thread will try to get in, but he will get the old value, which is equal to the new value of the first one, which is going to be unbound. Ah, poor guy. So he doesn't have the token. So the variable is unbound, he doesn't have the token. So T1 will do a wait, but old of T1 is the same as new of T0. So no token. And now assume T2 tries to get in. Okay, fine. T2 tries to get in. It also does an exchange. It has the old value, which is the same as the new of T1. It also does a wait. Poor guy. They all have to wait. They all are going to do or wait. So if you have 1,000,000 threads trying to get in, each one of them will get a new variable, and it will wait. Now, in the meantime, T0 is very happy, is executing P, and eventually is finished. T0 is finished. So he comes here, and he binds new to unit. And that means he's passing the token to the next guy. So binding new to unit means that T1 will continue. And T1 is now happy, and T1 continues. But T2 is still waiting. Huh? T2 is still waiting, and T2 will wait until T1 executes. So when T1 executes, it binds its new variable to unit, then T2 will get the token. So you see that each thread, when it comes in, by exchange, it actually gets a place in line, and the token means that the variable is bound. Okay, it's bound to a constant, and it will only happen when the previous thread leaves the critical section. So you see that the exchange is like the boundary guard. It's you're getting the token, and the wait is the gate which opens or closes. Okay, so as soon as this variable is bound, you get in, you enter, And then when you leave, you tell the next guy that you can go in. So each thread will basically pass the token to the next guy. Okay, so you see how that works? You see, it's a little bit subtle, huh? It's because it's a concurrent program now. We're handling many threads, and it's the exchange that is like the arbiter. The first thread calling the exchange is the lucky one, and they will enter in the order that they call exchange. So there's a question by Quentin. The question is, threads will enter in the lock at the same order they call the token, or order can be different? No, they will enter in the order in which they call the exchange. So when you call exchange, you get your hands on a variable and you wait until the variable is bound, and that means you have the token. So if you have 10 threads calling exchange, they will get 10 variables. The first one will get in immediately, the second one will wait for the first, the third will wait for the second, and so on. So they will go in the order in which they call the exchange. Okay, you see that? See how it works there? Okay, so let me go back to the slide. So I can actually write the code for that. So let me write the code for that. Okay, so here let me write a simple lock. Implementation of simple lock. Okay, let me call it simple lock because it's still not reentrant. Okay, we'll say so. The token is a new cell. The first one immediately has the token. Now we have a procedure. So this is the lock procedure with a zero argument statement in it. Okay. Let me first write the skeleton of this code. And then we have a record with let me call it lock with a field called lock. I have to put it in quotes because lock is a keyword, otherwise it doesn't work. So that's the lock procedure. Let me now write the lock procedure. I will do an exchange here of the token old new. Of course, I have to declare old and new here. And now I wait for the token. That's waiting for old. And now then I do P. And then I pass the token to the next guy when I'm done. News unit. Okay, so this is the simple lock, and it will behave like a lock, but it has a problem that it's not reentrant. Okay, so let me go back to the slides. Let me explain that. So let me go back now to the slide here. So the simple lock here, it purely does token passing. So, but it's not reentrant. And the reason why? Well, let's say that inside P, I try to go in again the lock. I could, maybe inside I'm also calling lock in here. In P, I can do that, like for insert 2. Well, what will happen here? It's very naive. The new second call will also do an exchange, and it will wait. But since it's in, it will never get out. So we have a deadlock. So in the simple lock, if you try to get in to a lock that you're already in, you're actually going to pick a ticket naively and wait for the token again, even though you already have it. So the system will deadlock, and it's a bug. Okay, so the simple lock does not let you stay in the lock when you're already in. So how do we fix it? Okay, we will fix it. First, let me do a small extension to simple lock. Let me add exception handling. So we want to make our locks completely good, realistic. Okay, I'm not showing you toy code. I'm showing you real code that you can use in a real system, which means that we have exception handling that can mess things up. What happens if P raises an exception? Wow, we have to handle that. Luckily, the try instruction can help us. Remember when we saw exceptions, we can do try finally. This means that this operation is done also when we raise exception. It's done in the normal case and in the exception case. So we will leave the critical section also when we raise an exception. Okay? So this fixes the exception handling, but still it's not reentrant. Okay? So how do we make it reentrant? We have to be a little bit smarter. A little bit, not a lot. We need a new concept. We need to know the identity of a thread. If I have each thread coming in, many threads, I have to know whether it's the same thread or a different thread. I have to know that. So in order to implement a reentrant lock, I need to know the identity of the thread. So different languages do in different ways. In Oz, I have an operation called thread.this. So thread is a module, and thread.this is a zero-argument function. It returns the identity, a constant, which is kind of the name of the thread. It returns the identity, and then we can compare and see if it's the same thread. Okay? So with this, we can make it reentrant. We need a second cell, which here I call it current thread, current thread, which tells me which thread is in there right now. And in lock, I have to put in an extra thing here. I will compare when I enter the lock, when I'm trying to get in, I will start by comparing the current thread with the identity of the thread that's trying to get in. If it's the same one, if the equal returns true, then I don't have to worry about tokens and whatever. I'm already in, okay? I only have to worry about tokens the first time I get in. If I'm in, I'm in, okay? So I immediately execute P and I don't worry about tokens. However, if the thread identity is false, if the equality is false, so a new thread is trying to get in, then I go to the else and I will run the code as before. There is small changes. I have to assign this current thread. So when I get in here, wait old, I'm in, I assign current thread to thread this, and before I get out, I have to assign current thread back to unit. So while I'm executing P, the current thread will be equal to the thread that's in there. Okay, so this is a correct implementation of reentrant locks. You see, it's still kind of subtle. And notice this, the order of the statements is extremely important. If I switch these two statements around, it's buggy. And you can invent a scheduler choice that will cause the system to do very weird things. Okay? So let me talk a little bit about debugging such a subtle implementation. So I have a question here. What can go wrong if the wait old and the cur thread assignment are switched? So going to the previous slide, it's this part. It's the coming in. And a second question, what can go wrong if these two instructions are switched? In fact, you are not allowed to switch them. If you switch them, it's a bug. So an exercise for you is to find a scenario. That means assume you have two threads and assume you have a scheduler that's trying to break the system, and you try to make the threads wake or sleep to make the bug appear. So the hint is that the wait must come before this current thread, and the new equal unit must come after, because the wait old means enter the critical section, and the new equal unit means exit the critical section. And the cur-thread assignments must happen inside the critical section. It must happen in a controlled environment when you guarantee only one thread can be there. So these assignments have to be done in the nice area, which means inside the critical section. Okay? So that's the theory of why they have to be inside. But a very good exercise for you. Imagine what could happen if these two instructions or these two are switched. What happens if cur-thread is changed outside of the critical section? Of course, if you assign cur-thread and then you do wait old, you can assume that it assigns the cur-thread and the scheduler sleeps right there. It wakes up the other thread, so the value of the current thread may be wrong. Okay? So exercise for you. Work it out. Figure out exactly how it can go wrong. And in order to motivate you even more, I can say that I could ask that on the exam. Okay? I could ask you to give me a scenario where it goes wrong if the instructions are switched. So this is a great exercise for you. Doing this exercise means you really understand how the scheduler has a power and how the program has to defend itself against the scheduler's nasty possible effects. Okay? Is that reasonable? So now you have seen the reentrant lock implementation. This is actually a quite subtle concurrent program. Okay? It uses token passing. It works correctly when an exception is raised inside the lock, and it is reentrant. So realistic locks are doing all this. This is a actually realistic implementation. Okay, for the reentrant lock, you see that? Okay, so that has given us already an understanding of locks. Let me show you now another concept called tuple space, which is another way of managing concurrent programs. So let me go back to the slides now. So now we have seen reentrant locks and we have seen how to use them. Let me now show you, to finish the course today, another concept called the tuple space, which is kind of halfway in between shared state and message passing. So the tuple space is not it's not a lock, it's a different thing, but we will implement it using locks. So I will show you the implementation of tuple spaces using reentrant locks. But tuple space is a very interesting concept by itself. Okay, so let me now show you what it is. So a tuple space is actually a data abstraction, a very kind of sophisticated data abstraction, which you can use for concurrent programming. So it's a multi-set of tuples. So basically, if I have a tuple space here, I can put tuples in there. And it can be stuff in there. So it's a multi-set of tuples. So a multi-set means that the same tuple can be in there more than one time. So it's not a set. In a set, each element can be in there only once. In a multi-set, you can have many elements in there, and the same element can be more than once. It's just that the order of the elements is not important. So the notion of set means that the order is not important. Okay? So we have three operations. We have write, read, and a non-blocking read. So let me explain the write. Write is very simple. You put in the tuple, the new tuple t goes in the tuple space. Read is also simple. You wait until the tuple space has a tuple with label L, and then you remove it and bind it to T. So basically you bring the tuple out. But you will wait until something is there. So the read is actually going to do a wait until the tuple is there. So if you want to remove a tuple, A34, for example, then you will wait first until there's a tuple with label A, and then you remove the tuple. So the read is actually waiting. So the write never waits. You can put tuples in there. It's like a big bag. And then the read, you can say, I want a tuple of this kind, and it will wait until somebody else puts the tuple in, and then it will take it out. Okay? There's also a non-blocking version of read, which does not wait. So read non-block. So it has an extra argument, B. It's the same as read, but it returns immediately. So B will be false if there is no tuple with label L. Otherwise, B is true, and it removes one such tuple. So the tuples are like unique things then. Each one I put in, it adds an extra element, and I can take them out one by one. So I really have a bag of things in a tuple space. So this concept, we will implement this concept using locks. So this is another example of how we implement something using locks. But we will also use it for building distributed concurrent programs. So just a little bit of history. The original concept of tuple space was invented by a computer scientist called David Gelernter a long time ago, in 1985. He called it Linda, not sure why. So for him, Linda is the notion of a tuple space. But in general, this way of programming is called coordination model. Why is it called coordination? Because you can have threads putting tuples in, threads taking tuples out, and the threads taking tuples out, they will wait, and the tuple goes in. And so they're like coordinating with each other. The thread taking it out has to wait until the other one puts a tuple in, so they're coordinating. So this approach of using tuple space is called coordination model, and a language that gives you access to a tuple space is called a coordination language. So this is actually an interesting concept that's sometimes used in real systems. Okay? It's interesting because it's actually a combination of shared state and message passing. Now, again, I'm introducing something subtle. So the tuple space is like shared state because the tuple space is shared by many threads. It's not cells, but it's a multi-set of tuples. And it's easier than shared state because a tuple is a big thing. So adding a tuple is like a large atomic action. You can add a huge amount of information when you write. And when you read, you take out a tuple, which can be very big. So it's much easier actually to program than shared state because tuples correspond to large atomic actions. So that's how it's like shared state. But how is it like message passing? Well, it's actually like send and receive. Writing a tuple is like a send, and reading a tuple is a receive. So a thread writing a tuple is doing a send, and a thread reading a tuple is receiving that tuple. So the tuple is like the message. What's the difference with message passing? Is that the sender does not know who is the receiver. This is very interesting. In a regular message sending, I send to a destination a message. I send to an active object or port object. But here, I send, but I don't know who is the receiver. The receiver is unknown to the sender. So the difference with message passing is that the sender does not know the receiver. Okay, so that's the difference. So it's a very interesting kind of message passing. You send messages, somebody will receive, but you don't know who. You don't know the receiver. So you can see tuple space is actually similar to message passing and similar to shared state. So it's a very interesting combined concept. Okay, let me actually, just to finish for today, let me show you an example of tuple space. Let me show you an example code. So there's a question: is the tuple space equivalent to the mailbox of Erlang? No, not really. The mailbox of Erlang is read by one process, whereas a tuple space can be read by many threads. That's one difference. So the tuple space is really shared data, whereas the Erlang mailbox is not shared. It's in each process has its own mailbox. Okay, so it's really inside the process, whereas the tuple space is shared by many, many threads. So that's one difference. The other difference is that the mailbox has an ordered set of messages. Ordered set of messages, and you read them in the order that they are sent in. But you read them with pattern matching, so that's the same. So tuple space in general, the read operation does a pattern match, whereas the mailbox in Erlang also does pattern match, but it's read in order. So there's two big differences then. Huh? Tuple space is shared by many threads, whereas mailbox is inside one process. And the second difference is that the order. A tuple space is unordered, whereas the mailbox is ordered. Okay? That answers the question. Let me show you just an example of running tuple space for finishing for today. So I have here very conveniently to the left a piece of code that implements tuple spaces. So the tuple space needs a queue. So I have here a queue, and I have here a class tuple space. So let me do a very simple thing. Let me copy and paste this code here into the Oz window. So here I have a special queue that is the queue that I've defined for the tuple space. And then I have the actual tuple space itself. So let me compile this. Let me compile the queue first. And now I will tuple space. So the tuple space is defined as a class. Okay. So this has been compiled. So now let me show you how the tuple space works. Let me just show you some possible operation on tuple spaces. So I can declare a new tuple space here. So let me run that. I can write things in tuple spaces. So here I will put foo of 1, foo of 1, 2, and bar of 2. Those are three tuples in the tuple space. And now I will read. Okay, I'm using a funny notation here, but let me change that. Local x in browse read foo x. Sorry, browse x. Let me write it in a way that does not use any syntactic shortcuts. So here I am going to read a tuple whose label is foo, and I will browse it. Okay. This shows foo 1. If I run it again, it will run foo 1, 2. Now if I run it a third time, the read will block. It will wait. Okay. If I run this now a third time, what's going to happen? What will be displayed if I run this a third time? While I answer that immediately, nothing will be displayed because the read will block. So it will block. You see nothing is displayed here. And now if I write another tuple, car5, nothing is displayed. If I write foo of 1, then the foo of 1 is displayed. If I write foo of 1 again, nothing is displayed. So you see, each time I do a read, it waits. Okay? Let me go back now to the slide. To finish for today. Okay, so tuple space. So let me just conclude. I will say a little bit more about tuple space and other things next week, but let me conclude for today. So to summarize, shared state concurrency combines threads and cells, and we have to manage the interleavings, exponential. And the way to do it is to build large atomic actions, and the main concept is a lock, and then monitors and transactions are refining that. We'll see that later. And we have also a very interesting way of doing shared state, which is called tuple spaces. So I showed you how to program with locks, showed some examples, and also how locks are implemented using token passing. And in the next lecture, we focus on monitors and transactions. So that's the end of the course for today. Thank you for attending the course. And so now you are free to leave, but I will stick around for a few minutes to answer questions if you have any questions. Thank you very much for coming here so early in the morning. There's the question, do I have information on how the exam will be organized? Yes. Yes, but I will give you the information. So the university, as you know, is completely reorganizing all the exams to be distance exams. So the exam for this course will very likely be a distance exam using a special software that will let you do the exam at home. And the software will basically check that you were not cheating. Okay, so this is still being worked out, but legally by the end of April, all the students will get official notification of exactly how the exam will be organized. So because of the coronavirus lockdown, we will not have in-person exams except in very special circumstance. So it's very hard. In the auditoriums, the students have to be spread out, and we need to disinfect the desks, and there's one entrance and one exit. So only a small number of courses will be in person. And almost surely this course, 1131, will be distance exam, except for a few people. So the PEPS students will still have in person because they're a small number, and there may be a few other special exceptions, but for most people it will be at a distance. But you will get official information of this by the end of April. So what I'm telling you now is it's still a part of the discussion. So the university is still working out the details. It's a huge amount of work, as you can imagine. So the university is being very proactive and working it all out. So by the end of the month, you will have the precise information. So there's a question, but I don't see the question because it's an image, but it's not. There's a question by Emar de Bukovan, but can you type in the question because I can't see it actually. For how many points will the project be worth? The project will be worth 5 points, and the midterm will not be worth anything. Yeah, the midterm is unfortunately not counting, but the project will be worth 5 points. So the exam will be worth 15 points. So please do your best on the project, and you will already have 5 points on your final grade. Okay, so the project is mandatory and will be worth 5 points of your final grade, and the exam will be worth 15 points. Okay, is that clear? So I don't know everything yet for the exam. I'm telling you what's known right now, but you will get the final information by the end of the month of April. That's a legal requirement, so the French community has made this requirement on the exams. So you will be informed well in advance, and we will also organize a test exam so that you can install the software and make sure everything is working fine before the actual exam. Okay, so don't worry about the software and making it work. We will make sure everything is working before the final exam.